Yes. Okay, so welcome everyone. I guess we'll get started. So this talk, I just wanted to introduce some methods that we use amongst our lab, using it primarily it's an introduction to econometrics. And it's really targeted for people who haven't done econometrics before or not familiar with these methods. So it's very, it's based on a lot of my classes, my 5,000, 6,000 level classes, all condensed to about an hour and a half. So if you've done some econometrics before, you've done some, these models, and this would be a very simple introduction, very rapid introduction. But if you haven't, then it's hopefully can help you kind of think about the framework and how we can think about data analysis. And at the end, I really want to focus on is to, and at the end, then I really kind of want to give you a couple of prescriptions on how to use some of these techniques for the different contexts. So, so let's kind of jump right in. Okay. So again, the introduction is really for non-social scientists to introduce them to how social scientists think about data, really historical data. Right? And the goal then is to introduce this causal framework on analytics. I'll just kind of use analytics as a general term to mean kind of this econometrics approach to this. And then I would talk about some of the common tools and techniques, and then really end with identification and a couple of examples of how to use these techniques on our data sets. Okay? And again, this is really a very condensed version of my 5,000, 6,000 level modules. So it's a little bit, if it's too fast, just slow me down. If it's too slow, then I'll try to speed up a little bit. Okay. An excellent book is this Mostly Harmless Econometrics book. It's kind of a condensed version of the more extensive textbooks that we use for the econ classes, IS classes, and whatnot. Okay. So first, let's kind of quickly do a quick review of linear regressions. And also, if you're not familiar with, then this is a great kind of introduction to this. So the idea of a linear regression is it's a statistical tool to predict or explain one outcome, sometimes what we call a dependent variable, of multiple, one or more, what we call independent or predictor variables. Okay. And it's really quite commonly used, especially when the dependent variable, the outcome variable, is continuous. So it could be like income, it could be like your grades, right? It's not like a binary, or it's not discrete. So it's not like a yes or no, did I pass my class or not? It's not like a maybe which category of clothes of item did I choose. It's not that type of work. It's more just a continuous outcome variable. Okay. So in general, it's really primarily been used for predictive modeling. But what we want to talk about here is how can we extend this potentially using this tool for more causal analysis, and some of the common techniques that we can use for that. Okay. And so, but the overall idea of linear regression is really it's based on correlations. Try to outline different correlations between two or more variables. Okay. And so usually, typically our data then is represented as a matrix, as a table, right? And each row is an observation or a single entry into our data. Okay. And each column then is sometimes known as like a variable. It could be like our dependent variable or our independent variables. Okay. And our observations can then represent certain different things that we're trying to model. So for example, we might be modeling students in the classroom. So that would be one observation. Or it could be students engaging in the tool. So an observation here would be one student and that session in the classroom. That would be a single observation. Okay. More generally, of course, it could be like countries and companies if you're doing more general form econometrics. Okay. So here, so when I say it could be a tuple, it could be a user, a transaction, or a company, a time, or even more extensively, multiple ways of outlining a single observation. Right. Okay. On the other hand, a lot of times we try to simplify things by traditionally data has been more cross-sectional, where it's just a single time slot. It can be collapsed, like how the student performed, what's the grade that the student received in this whole semester, or perhaps their whole 4 years at university. That's cross-sectional, right? But I want to argue that with the increasing data quality, we can actually get much better time series or panel data, right? Where there's multiple observations of the same unit. So you can observe the student every semester, what the grade they received, even more granularly, perhaps every lecture. And now we're actually seeing like time stamped to the millisecond of what the student is doing on these platforms. Okay, so I'm going to focus a little bit later on how we can use these panel data, a little bit less so on these cross-sectional data, because I think that's going forward. It's going to be a lot more of these massive panel data sets. Okay. So, but anyways, before we jump that, let's kind of go back to linear regression models again. So here is simple, let's say cross-sectional with single time period panel regression model. You have some y, which is really, let's say, a whole column of different y's. Each row is, let's say, each student. And you have some x's, which could be their age, their gender, maybe their grades, right? And then we try and model it using this linear expression, where we have alpha, which is simply just the intercept. So you should go back to like your linear algebra days. Right? Alpha is the y-intercept of some line. Okay, and then you have the beta 1 and beta 2, or more than 2, which are the slopes of this line, this trajectory. Okay, and then when we model this, we're going to get some sort of error term. So we're trying to find basically a line fits through our data points, which will also include some sort of error for each observation. Okay. So the objective then of the algorithm, of the linear regression algorithm, then is to try to estimate these alphas and betas to best fit the data. Okay. And I keep on saying algorithm because that's essentially what it's going to do. It's like a little bit of a black box, not fully. I mean, there's a lot more technical assumptions involved in this. But we'll try and find the best alphas and betas to fit the data points in what you have observed. Okay. So let's try and visualize this a little bit. So let's say here we just have a single x variable, and the outcome variable y on the y-axis. Okay. So each of these points is an observation. So if you look at your Excel sheet, each of these dots is a row. Okay. So plot this on a two-dimensional space. You have here's 1 point, 2 points, and so forth. Okay. And so what the regression model tries to do is try to find this best line that somewhat fits all the points. Okay. And it does this by finding this alpha, the y-intercept, and the slope for beta. I mean, and the objective then is to try to minimize the error, which will be defined as the difference between these points and the fitted line. Okay. So this is known as sometimes the least square criterion, where we can define this error term as our y that's observed minus this alpha and beta that we predict. Okay. So you look at back, it's really along the y-axis, the difference between this point and the line. Okay, and we're trying to find the alpha and the beta to minimize on this distance. Okay, so that's what this equation says, and we're going to square it just to kind of remove any positive, negative signs and penalize if it's further away from the line. Okay, so the algorithm will essentially try to find these alphas and betas. Okay? I would say algorithm because at the end of the day we tap into R. That's essentially what we're going to do. But our objective, however, is to try to model this in such a way that we can get more causal inference from our data sets. Okay. Okay. So a lot of software then will kind of give you a couple of interesting statistics to explain how good a fit it is. So one of them is something known as an R-squared, which is simply just a ratio of the variation of x divided by variation of y. So basically it's saying, is our line actually fitting and explaining all the variation in our data set. Okay. So the R-squared then should be a value between 0 and 1. So if the R-squared is 0, the software will report to you what the R-squared would be. If it's 0, it just says, this is a really bad prediction, there's not a very good fit. Okay. If it is an R-squared of 1, it means that the data is perfect fit. All your data points are perfectly on the line. Okay. In practice, I think you rarely ever see an R-squared of 1. If you do, I really question your data set. Okay. Just a slight variation on that is sometimes known as an adjusted R-squared, This is a little more of a technical point, that basically the more predictors you have, generally you have a higher R squared, lower R squared. But then this adjusted R squared then would just normalize it so that you can have different models with different number of predictors, but you can compare it against the same metric. So what that means is that sometimes you have a model that has like maybe 1x, another model has 2x's, another model has maybe 3x. How do you know which model to use? And one of the guidance is to using this R squared. Okay. So basically you want to find a model that has a higher R squared. Right? The adjusted R squared would kind of normalize across the number of predictors you use. That's the main point of this. Okay. But that said, what we focus on a lot actually is more about the individual variables that we use. Are they good predictors? Are they a good fit? Specifically, we want to know if this particular beta on this particular x is a good predictor. Is it statistically different from 0? Right? And this is going to be very useful for hypothesis testing. Okay, so if a beta is 0, it's suggesting that x is not a good predictor at all of our outcome. So it's statistically insignificant. Okay, but if our beta has a t-statistics that's greater than or equal to 1.96 or about 5% significance level, then we have pretty good confidence that x is a good predictor of our outcome. Okay, so it's a little tricky here because actually it's a double negative, right? We're going to be very cynical and very skeptical in saying that we believe our x is not a good predictor. That's our baseline. So now if we think that our x is not 0, then we have some confidence that there might be an effect there. All right, so it's kind of like the Fisher type of model here. Okay, so that's the interpretation. Is that so? We're looking for a t-statistics of greater than or equal to 1.96, or sometimes known as a p-value that's less than or equal to 0.05%. Okay, and so the interpretation then is that if beta is statistically significant, if you increase x by 1 unit, you would change y by beta. So beta could be positive or negative. Okay. So in the interpretation of the alpha then, of the intercept then, is it's in absence of any x, this is your average effect. Okay. Okay. So this is an example of some outputs that some software typically will produce for you. Here, I'm taking an example from marketing, some sales. Here, the y is the number of units that you would sell, say, an item of clothing, and then you have the price of the piece of clothing, and then whether it's on promotion or not. This is a binary 0 and 1. Okay. And in the first column, then, is that you have the beta estimates. Oh, so the intercept here is the alpha. So this is the beta estimates. It reports to you the t-statistics and then also the p-value. So again, if the t-statistics is greater than absolute value of the t-statistics is greater than 1.96, then you can say you have confidence that it is a good predictor. Okay. Otherwise, I also look at the p-value. It's less than 0.05. So here in this model, what you see is that price is a good predictor because the t-statistics is greater than 1.96 at the absolute value, and the p-value is also less than 0.05. Okay. So here in this model, price is a good predictor of how many units of clothes are sold. Okay. On the other hand, whether it's on promotion or not, this is a 0.1. The p-value is greater than 0.05. Right? And the t-statistics is much less than 1.96. So here, whether it's on promotion or not, is not a good predictor of the number of units of clothing that's sold. Okay. So that's how we can interpret that regression models. Okay. But the real challenge to actually all this is not so much the real challenge is actually more about understanding the model and how to do better modeling. What variables do you put in? Sometimes you might have many x's, and how do you choose it? Especially if you're trying to investigate some hypothesis or some sort of causal factors, right? But to understand that, then we need to understand some of the assumptions that are built into the regression model. So one of them is that there is an assumption that your x's are independent. there should be no correlation between x1 and x2 in the ideal world, or very little correlation. And you'll see later on that that is, in many cases, that's not true. And if that's not true, then our regression models may not cannot infer too much on the values, on the betas. Okay. Second assumption, of course, is that it is linear, so that you're assuming that y is some sort of a linear function, right? And x is also some sort of linear function. So that means that if, let's say, more money makes everyone happier. Okay. Sure, everyone believes it's kind of happy. After, like, if you're Bill Gates, adding another $1 million here and there probably is not the same to adding $1 million for you, right? And on our professor salaries, okay, right? So in that case, the function may drop off and might taper off, right? It's never, for Bill Gates, it's probably not going. It's not going to go negative. Extra $1 million is probably not going to be negative for him, but it's still not linear compared to us. Okay, so that's what I mean by it's a linear assumption. So in some cases, if you think your data is only within a certain range, then a linear might be fine. That's fine. Okay. So we also, this is a little bit more technical term, is that we also assume some sort of constant error term. So you go back to this figure, we look at here. The error is, again, the distance between the point and the line along the y-axis. We're assuming that overall the error somewhat is in this band that's consistently as x goes to infinity, right? But that may not be true. So it might be like some sort of like V-shaped, funnel-shaped, where as you move further x, then your error might get larger or smaller, and that's going to be a problem. Okay. But that's okay. Yes. And then we also assume independence of error terms, and we also assume that most of our variables are normally distributed. Okay. So some quick takeaways is that if with these assumptions, at least if it's not normally distributed, you can do some simple transformation to make it look somewhat distributed, normally distributed. So it's very skewed. Then you take the natural log of the variables, and more or less it will work in practice to make it look almost normal. Okay. Of course, nothing is perfectly normal, so take this with a grain of salt. Okay. Okay, but I want to kind of jump here then. So again, the overall objective that we're trying to do is to try to infer some sort of causal analysis between two variables. Okay, between x and y in the simplest case. There's one variable that will cause. So causality is actually a really interesting concept because it says if you change x, you can guarantee y will change with a certain confidence. Okay. But otherwise, if you did not change x, then y will not happen. Right? So kind of motivate this a little bit with a quick video.
Mission is all that's going on there. Now, Donna, you got quite the event today. It sounds like what's going on with you.
Well, I wanted to voice my opinion on something that's been bothering me for a really long time.
Okay.
I tried writing a newspaper and contacting TV stations, but nobody seems to want to stay with this. So that's why I'm calling you guys. Okay.
What's the issue?
Well, over the past few years, I've been involved in 3 separate car accidents involving deer. The population and everything. Each of these incidents, they occurred shortly after I saw a deer crossing sign on the highway. Well, my frustration is that Minnesota and North Dakota Departments of Transportation would allow these deer crossings to be in such high traffic areas. I mean, I've even seen them on the interstate. Why are we encouraging deer crossing the interstate? I don't get it. It's a high traffic area. I mean, I understand that deer are wild animals. They need to travel across the streets occasionally to survive. And now, of course, there's find food, but it seems to me that so irresponsible of us to allow these deer crossings to be in areas where these deer are so likely to be struck by oncoming traffic. Wouldn't you agree? I mean, it's just, I mean, you think they would put deer crossings maybe, in smaller town, maybe doing it like at a school crossing. It would be a safer place for them to cross.
Wait.
You know, the deer crossing sign.
You know, deer crossings aren't telling deer that it's safe to cross there. It's just more of like an alert for drivers so they know it's like a high deer population.
But there aren't the deer crossings there. They can direct the deer population anywhere they want to by moving that deer crossing sign. I mean, you know, why in the world would they place it on the highway or the interstate? You know? I mean, God, there are so many other places I can think of than to put the deer crossing signs on busy highways and interstate.
You seem to be under the misunderstanding that the deer are somehow attracted to the deer crossing sign.
Well, yeah, the deer crossing sign is there to allow the deer to know that's where they need to cross.
Right. And all these car accidents you had involved the deer after you saw a deer crossing sign.
Exactly. I mean, I'm trying to watch out for the deer, but I mean, you know, even at 55, 65, how am I supposed to, you know, you can't brake really quick if you know, if the deer is crossing in that deer crossing area.
So you'd like to see these signs move somewhere safer?
Right, we can move them, like, don't put your crossing signs on the interstate or freeway, you know, put them in lower traffic areas. You know, somewhere where the speed limit is, you know, a lot slower, you know, maybe small towns, I don't know. I think school crossings is a good idea.
Well, listen, we will, yeah, I mean, you say you tried to contact quite a few people about this.
Right, yeah, I wrote 3 or 4 letters and...
We will spread the word, okay? We will try to kind of help you raise some awareness for this issue, okay?
Oh, thank you. We need to move those deer crossing signs.
We appreciate you coming this morning.
All right, thanks.
Bye. 237 hits, you text 4933.
So I think that sometimes, you know, we, when we analysts and we, maybe good intention, like this woman, right? She sees 2 events happening with high correlation, deer crossing signs and and car accidents, that, you know, if we just kind of blindly do the analysis to understand the causal models, we may have different outcomes or different interventions to kind of change what we want to do, right? So I think this is the point I'm trying to make here, is that, you know, she's very intentioned. Actually, she followed up. She's a very sweet lady. It just didn't have much experience with deers before, right? But I think that for any type of data analysis, we really need to be careful about the context and really understanding a little bit more. Okay, so there's actually kind of a fun blog that I follow about these really spurious correlations. It's correlations that just kind of happen in nature, that you not in nature, but that you see it happening, right? And people blog about it and talk about, like, you know, this is one of the you should be a little skeptical. We're talking about like big data sets or like any sort of big data, really. So one of them is U.S. spending on science-based technology highly correlates with suicide by hanging, strangulation, and suffocation by about like 99%, right? So science makes people suicidal. Number of people who drown by falling into swimming pools, it correlates to the number of films Nicolas Cage made. Divorce rates in Maine correlates to per capita consumption of margarine, right? Age of Miss America, highly correlated to murder by steam, vapor, and hot objects. Not sure why that's happening. And then one of my favorite is Internet Explorer. It has correlated 99% with U.S. murder rates. So, you know, it's a really frustrating browser, you see. You need to take it out somehow, right? So my point is that, you know, when we do all this analysis, we should really be careful about correlation versus causation. And actually, with more data sets, you can almost find a correlation with almost anything, right? And is it meaningful or not is the question. Okay, so yeah, this is this is the website I'm quoting for. It's quite a bit of fun to look at if you're bored. Okay, so sometimes I also think that with our data is we're a little bit like these blind men trying to understand the elephant. Right? As the saying goes, you know, there's this elephant, and 3 blind men try to come and describe what the elephant looks like. Right? Our data is not complete. Our data doesn't totally tell us the whole picture, but we're just going to try to feel around and make some interpretation and make some conclusions based on what we can feel in our area, right? So more typically, I'd say like we really have a data iceberg as a problem. So what we see above the water is, of course, it is large amounts of data, massive data sets. It is quite cumbersome to work with. It indicates that there is an iceberg, okay? But sometimes it's sufficient to just know that there's an iceberg underneath, okay? But many times it really is not. So you're trying to navigate a ship, you see an iceberg very far away, you know to somewhat avoid it, fine. But what you don't see is actually the stuff that's underneath the water, the data that we don't collect, okay? And what we see then, it's a lot of unknowns. It's much larger than what we have. It requires lots of support, but it is required to support what we see above the water. So something about the generating process underneath the water that's actually going to reveal the data that we see, that we are collecting. Okay. And so really we need a holistic view, because by understanding, like say, fundamentals of physics, of water, of crystallization, then we can understand what we see above is a result of what's underneath. Okay, so then we really need to understand the underlying process that generates ice, so that we can see the iceberg above to interpret the overall iceberg, a holistic view, so we can take the appropriate actions. Okay, so again, the deer lady example, the woman wasn't familiar about deers, she didn't have the whole picture. Okay, so I think a lot of times where we see the data field, especially in Singapore globally, is that people tend to confuse prediction and causality. And really, regression and prediction is primarily based on correlation, finding patterns through correlation of some sort, where it's linear, and you can slice it in different ways, fine, but is it really a causal? And in some cases, yes. Okay. So for example, typical marketing examples would be like, say, market basket analysis. You want to buy, sorry, I use a lot of marketing examples because my training is on marketing. So we look at a lot of retail sales. Now we're moving into more like education, right? But in retail sales, what people have seen in the past are beer and diapers. So one of the most, if you look at the shopping baskets of people when they check out, most common items together are beer and diapers. Right? Why is that? You have a lot of drunk babies going around, right? Not so much, right? But it might be a couple of theories. Maybe it's because the father's going to get some diapers and then also buying some beer, or maybe vice versa. Okay. So prediction then will show that one is good prediction of the other. If you buy diapers, you will also buy beer. If you buy beer, you also buy diapers. But then is that going to be good enough? Right? So for the retailer, they say, well, what if I promote one? Will it get the fathers to come in to buy the other? Then what is it the intervention I should do? Should I promote beer or should I promote diapers? Okay, and that's not so clear from our regression models. Okay, and so ideally, the best way to do this is to do some sort of A/B testing, doing controlled experiments, randomized field experiments. Right? Maybe in some stores you promote beer, in some other stores you promote diapers, and see which one results in more sales in the basket. Okay. So this is, I guess, where Joseph is very good at, is running a lot of these field experiments. I'm more of a data person. I do less intervention, trying to still pull out these inferences. Okay. So okay, we talked about that. Okay. So we try to promote one or the other. Okay. Okay. So this examples. Right. And then the easy analysis here then is simple. If you have a good intervention, then you can just do simple t-tests. Right. A lot of pharmaceuticals just do these interventions in a very controlled manner, and then the analysis is much simpler. Okay. And R just do that with a one single command. Okay. But let's take this mental challenge for example. Okay. So instead we don't have interventions, but we have just observation of historical data. How do we still get inference out of this? So let's assume then that we're going to try and model these behavior of these students, let's say, as random variables. Okay. So now let's say we're going to try and model it as x Y, and W. Okay, and we believe that here X could be educational attainment, number of years you've been studying, and Y is income, how much money are you making? Okay, and W is some sort of ability. Maybe you're just inherently born of like a larger brain size, or you have other confounds, right? Your other abilities. But the problem is that so our goal then is to try to create a causal link between X and W, or sorry, X and Y. Basically, as a policymaker, MOE, Ministry of Education, says, well, what if we just ask people to take more classes? Okay, is that going to drive higher income? It's a very causal inference that they're trying to make. Okay, but the challenge here is that a lot of times, even at the university, we can change this, certainly, no problem. But we cannot necessarily observe W very well. Right? We have some proxies, maybe some test scores, and previously we have all these other things, but still, maybe if you look at test scores, maybe test score is actually a function of how much educational attainment they put in, how many tuition, how many tutoring hours to put in extra, right? All these other factors. So we cannot really observe W very well. Okay, so W then we like to say is that's what's under the water of this data iceberg, where we see X and Y. Okay. So now I'm going to try to simulate this just as a mental exercise, see what happens. Okay, so we're going to say, okay, we're going to generate 100,000 students. This is our code, and then we can generate our W, which is some sort of normal distribution, okay, of students' ability. And then we say X is, we can say that of course W affects X. Maybe the smarter you are, the more capable you are inherently, then you get into certain tracks. You get into advanced programs. You can do more. You can go into finish college and PhD and so forth. Okay, so W affects X. X also affects Y. Then W also affects Y. Okay, so we can simulate that by saying X equals to, let's say here 0.5 of W plus let's say some sort of noise. This is our epsilon. Okay, and now our Y then is 0.3 W. Plus 0.4, let's say X, and plus noise. Okay, so that's our model. So now, again, we don't know W, we only know X and Y. So what happens when you run our linear regression model? So here our model is this X and Y. If our models work, then we should get back the coefficients that we put into our model, right? So if our model is correct, we should get a beta on X as 0.4. And as W is 0.3. But here again, we don't have W. Okay, but you run this model, and then I'm going to try to run a comparison of the real model where we do have W. Okay, so what do you find? First off, with the incomplete model, our X is completely bogus. It can actually be 0.5. We're not even estimating the correct value. Okay, but it's statistically significant, right? So this is very disturbing because this is the only data we have. We're trying to estimate it. It thinks it's correct, but we know from the simulation we put in the correct value, it's not able to reverse the function properly. Of course, if we have W, then this all works out very well. Okay, about 0.397, 0.4, right, plus some noise, and then we estimate W correctly as well. Okay, so I think this is a very big problem for us because we need to somehow then account for our missing data. Okay. Let's look at another example, which kind of illustrates this even further. So we're going to look at this type of network where X affects W, Y affects W, but X affects Y. Okay. Right. And so this example might be how much do you, so X is educational attainment, Y is income, and W is how much you spend on, let's say, fine art. Okay, you have to buy fine art. Okay, and here you might say, well, if I'm very, very well educated, maybe I appreciate very expensive art. Okay, but of course, if I have income, I can also buy more art. If I have a lot of income, I won't be able to buy a lot of art. Okay, and so we generate our network again. So we do our X as normal distribution, Y is 0.7 you have x plus noise, and W here is then, let's say, 1.2 of x and 0.6 of y, just arbitrary numbers I threw in, okay? So we simulate this, we back it out. Now let's back it out with the incomplete data, where we just y is a function of x, and then with the complete model of y of x and w, okay? Same thing as last time. So now what do we get? So here, with the incomplete model, you get x is estimated to be 0.7, right, which is correct. But with the complete model, supposedly, then we get x as negative 0.01, right, and w is 0.43. Right? This is completely bogus, but you might say this is okay because this is not the correct model anyways, because this model is implying that w affects y. So this is not completely correct either. But what is more disturbing, however, if you look closely, is our R squared. So R squared here is, again, trying to see how well it fits the data. Okay, and this should actually be our correct model because only x affects y, not w. Okay, but our correct model here has a fit of R squared about 0.33, but our incorrect model here, where it says y is causing, or sorry, w is causing y, actually has a better fit at 0.5. All right. So here, actually, our incorrect model is telling us it's a better fit than our correct model. Right? Is that so clear? So this is the incorrect model because the direction of causality is not correct. All right. Okay. Yes.
So is it adjusted R square or just R square?
Well, so both really. So adjusted R squared here is reported as 0.5. Multiple R squared is also 0.5. So it's more or less the same. Right? So we can compare adjusted R squared or to adjusted R squared or regular R squared to R squared. But good point, right? But still, you're talking about 0.5 versus 0.3. Still a valid large difference. Okay. So this is, again, this seems to be a better. The algorithm says this is a better fit because this is all correlation, right? They do show that W is highly correlated to Y. And it should be. Okay. So these are known as colliders. Adding in wrong model specification, but adding in extra variables to give you a better fit. Actually, it's the incorrect outcome. Okay. Okay. So can I back up then? So how do we think about causality? So in historical data. So so one is that we define some sort of treatment, right? Some sort of factor that can cause some sort of outcome. Whether you're manipulating like maybe a MOOC, right? Or some sort of feature in a MOOC, or maybe you have some policies in the past that you implemented. That's the treatment. And in this case, it could be like testing drugs to cure cancer. Okay. In A/B testing, you just say, okay, it's double-blind. You put the treatment in the treatment group, and then the control group should be the same in every other way before they enter the experiment. Then we report the results after the experiment. Okay. In social sciences, the treatment then could be exposure, it could be pricing, it could be information, it could be some sort of social influence. I put a star here because a lot of my research is on social influence. It's actually a very technical term. So I know in the education context, there's quite a lot of interest in social influence. But what I mean here is it's a very causal claim, meaning that I became one of my postdoc Sheshang came in. So let's say Sheshang influenced me. When I say Sheshang influenced me on something, that really means that somehow he persuaded me to say adopt an iPhone or get better grades. Okay, but if he wasn't there, that effect would not be there. Okay, but that also makes a lot of different assumptions. One of them is that why did I choose to become friends with him in the first place? Then how do you control for that? Right? Maybe I became friends with him because we both have high grades. Right? So we become friends. We have a lot of outside activity. It's not really influence that we're seeing, but it's actually correlation. Okay. So those are some things that the technical definition of influence is quite strong. And if you're doing a lot of social networks, it is a causal claim. Okay. But you cannot list all the different treatments that we can look at. Okay. Okay. Let's see. Sorry, I'm trying to skip through this. Okay. So the other benefit of sometimes where we need to use data for influence is sometimes it is hard to conduct these or manipulate these experiments. because of social or political factors, right? Because of maybe legal reasons, engineering reasons, IRB reasons, we need to rely on variations in the past. So one example is I have a paper where we're looking at how the relative age cutoff of students affects their outcome, right? So we're saying, you know, if you have a cutoff date for entry into primary school, then the ones who are closest to cutoff are the oldest. The ones who are towards the end will be the youngest. So there's almost a year difference between the oldest and the youngest student in the same cohort. How does that affect their academic performance, right? It's very hard to do an experiment on this type of policy because you're going to imagine all the political implication for this. So we need to look at historical data and see different variations. So in this particular paper, what we looked at was actually the Chinese Cultural Revolution, where schools were abandoned for a few years and then reinstated, and then strict cutoff rules were reinstated decades later. Okay, that's a separate topic, but I'll get to that. Okay. So we try to really find post hoc evidence. Okay. So can we still do this, and can we really apply the scientific method to try to isolate this causal factor? Okay. So we need to form a hypothesis. We need to isolate the treatment, and not affected by observables and not unobservable confounds. Okay. And we really need to kind of somewhat avoid confirmation bias, right? We need to really be very skeptical about our analysis. Okay, I want to get to something a little more practical here. Okay, so real model then is that entities are really a random variable and a random process. Okay, it does empirical methods really capture, as you saw in our examples, be able to reverse these parameters and come out of it, okay? And does it support our hypothesis? So what can go wrong? One thing is selection bias. Maybe students very pre-selected into certain programs, right? So technically that's saying that before the treatment, so your outcome variable is highly correlated to being assigned to one group, the treatment group or not, right? So for example, if you're looking at, like, you know, that's called university education increased income, a lot of students are very pre-selected. Only more capable students with higher grades are selected to attend university. So maybe even about the university, they will be getting higher income regardless of the university. Right, so that's a selection bias. Another example is if you had to choose between two hospitals, hospital A and hospital B. If hospital A had 50% death rate and hospital B had 30% death rate, and you're critically ill, which one would you choose? 30%, right? But the problem is that maybe hospital A is actually better at more critical conditions, right? So that's the selection bias. Okay, and of course we talk about confounds and colliders. A more technical problem is also what's known as endogeneity, which I think we have some of our econ colleagues here. They spend a lot of time on this area, but it's essentially kind of boil it down into one bullet point, is that there might be some unobservable process that's internal to what you're trying to model. It's a function of something else. Okay, and you cannot tease out you cannot separate the parameters very well. Okay, because causality really requires some sort of exogenous assumption. Meaning, if I'm a student, if I already know that going to college will affect my income, whatever actions I take has already taken into consideration that future-looking behavior, right? Only if suddenly, you know, let's say I'm a very bad student, suddenly MOE, Ministry of Education, says, no, we're going to randomly draw some people, and you're going to go to college no matter what. Right? And we're going to give you funding and everything so you can do it. That's going to then draw a stronger causal influence on the benefit of education on income. Okay. So we can still try to work with all these conditions. We can still try to work for causation in certain conditions. Okay. So inference then is knowing what kind of the inference then is really kind of see what kind of conclusions can we make, what kind of policy recommendations can we make. Okay. But it requires quite a bit of domain knowledge. Okay. And it is plausible. If it wasn't plausible, I guess we wouldn't be here. And in practice, you really need to know, we should know by design whether causality is possible. So even before you start investigating into a project, you should say, okay, well, if this is the type of data I have, these are the type of conditions that we have, then using some of these techniques that we're going to cover today, then causality may be possible. Right? You want to do this even before start data cleaning, because that's going to take a lot of time to data clean and dive into it. Okay. And some of the things that we care about is data availability. What kind of granularity do we have? Is it like annually data? Is it like, by cohort, 4 years, or is it like by milliseconds? Because then that can give you a better idea of what these methods you can use. Okay. Data quality, and possibly other constraints. Okay, and it really is an iterative process. We keep on having to try one model, it doesn't work, we have to tweak it, we have to modify it, and try to possibly collect more data. Okay, so let's just take a look at different types of data set. So I mentioned one was the cross-sectional, where we have, like, let's say student after 4 years, what's their GPA? That's not very so nice. Nowadays we have a lot more panel data, where we have the same student where we can observe over multiple time periods. Okay, so we're using like a MOOC. You really have millisecond timestamps of everything that they did, what they saw, the impressions. This is from like the clickstream logs, the Apache logs. You have the timestamp of when they posted or created new content on the MOOC, right? So you have quite extensive data. So big data is quite big because you have a lot of users and a lot of observations over time. Okay. So typically, it might look something like this. Here, this is an example of country. You have country ID, country 1, 2, 3, 1, 2, 3. You have observation, 3 years of observation for each country, and then you have some sort of Y and then some sort of X's over them. Okay. And what we're trying to argue is that panel data gives you a better view into causal analysis than cross-sectional. Okay. If you map out, if you just visualize this data, it might look something like this. For each country, it might be like one of these colored lines. It might be up and down. Okay. And so it's nice because what we can view is that each entity is like its almost like a parallel universe, if you wish. Right. Each individual student you observe over time, you can see how you can control for the individual student's abilities in these what's known as fixed effects. Okay. And also observe how different interventions can change the average of all the students, as well as individual students and subgroups of students. Okay, and so what I want to say then is the outcome. We're going to subscript that by I. I is let's say student, and T is each time period you have. Okay, so IT, and we have a number of different predictors. We have time varying predictors, which are XIT. It does vary over time, and then we might have some types of time invariance, but sometimes known as these fixed effects. So time invariance may be like, say, gender. Most people don't change their gender over time, right? I guess maybe Thailand is a little bit more often than others. But if it doesn't change over time, it's very hard to kind of have some sort of strong belief that it has an impact on the outcome, right? It doesn't change. There's no variation, okay? And so a lot of these panel models can also, of course, drive a better fit. Okay, oops, sorry. The slides didn't work out that well. Okay, so let's take an example of a simple treatment in a panel model. So you have some sort of treatment row, and you have some sort of outcome with or without treatment. So in one group, you have Y. I'm a subset is 0T, means this is the control group. This is the treatment group, YIT, which is randomly treated. You have some sort of time factor of that individual, and then you have individual time invariance. Okay. And therefore, what we can say is the expected outcome of the control group may be given by our model, some alpha, a baseline, an average, and then the time factors, so let's say weekly, and you have individual time invariance, and maybe some other factors, and finally Rx. Okay. If both groups are the same, then really the causal effect should be the same as the top equation, which we have here, plus the row. Okay, and that's our claim. Okay, when we think about it from a random variable perspective. Okay, so then our estimation is actually, our analysis is actually quite simple. We just say, look, if you just take the time difference between time 1 and time t and t minus 1, any difference you see, right? Oh, sorry, let me back up. I jumped ahead a little bit. So then our model simply just tries to estimate this type of model in R. So we have y basically equals to alpha I plus lambda t plus our treatment, which can be dummy, like 0, 1. This person was in the treatment group. This person was not in the treatment group, 0, 1 for each individual. And then xit. So I said dit, this is a dummy variable, 0, 1. I said it because technically you can have someone be in the treatment group and then at some period of time the same person not be in the treatment group later. Okay. Usually it's a little bit more simple than that, right? Either they're always in the treatment group or not. Okay. But this is just a more general formula for this. Okay. Oops. Okay. So that's our estimation model then, cleaned up a little bit. It's the same thing as the previous slide. And so then we can also model the different changes. This is the change over time between 2 time periods. Okay. So the change in y is, and the change in the lambda, the time variance, plus the treatment and the change from one period to the next period, and also the change in the exits. Okay, so this is a slightly different interpretation using difference models. Okay. So let's take a little more concrete observation on this. So what we're going to say is this is again that country. We're going to look at different countries, different over time, but we're going to look at it from a simple, not panel view. Okay. We just have each row as just like an independent data point. Okay, and we try to fit our model, and we get some sort of line. I would say pretty bad fit, right? It's just a lot of noise, a lot of whatnot. But now, what if we add in the country variables, the fixed effects? We track each country as its own group, if you wish. Okay, and then try to refit the model. So this is again, this is the analogy to this for students is, you know, you have students' data, all 30,000 NUS undergrads over 4 years. So we have 120,000 observations. We just plot 120,000 observations as scatter plots, and we try to fit some sort of line. Right? Not so good. But now we're going to try to follow each student and see what happens. Okay? So we can do this by 3 different ways. One is we just simply put a dummy variable for each group or each student. So is this student number 1? Yes, no. Is this student number 2? Yes, no. Is this student number 3? Yes, no. So we have almost 30,000 dummy variables, 29,999 unique n-1 dummy variables. Okay. Then we talk about the fixed effect models and then random effect models to do this. Any questions so far on this? Okay. So if we do the same plot, but now when we plot it, basically now we have this one student. Now we can see that it is on its upward trend, another student upward trend, another one, and so forth. Right. You see that this is a very different view than what I showed you just 2 slides ago. Okay, and this red line then is what was predicted before, outgrouping them into individual students or countries. But when you do, then what's the trend line then is much more obvious. It's more, the slope's much steeper, and the effect is much stronger. Okay. Okay. So if we do the dummy variable approach, I'll just kind of show you very quickly. This is the R code. You want to do that. You put a dummy variable for whether it's in this case country, like country ABC or student ABC. Okay, it will estimate basically each of these student factors is just the student average or their known fixed effects. Right, so anything that's time invariant about the student will be thrown into this coefficient. Maybe it's their gender, maybe it's their height, maybe it's their IQ, whatever it is. But we really cannot separate each of those factors from the time invariance, from these fixed effects, because there's too many of them, they don't vary. So how do we know it's the gender or it's the IQ or the height that's actually contributing to this? We don't know, okay? But if we run it as a dummy variable here, what we see is actually we focus on this x1. We see that suddenly our coefficient becomes quite significant. So we go back a couple of slides, you see here, we try to estimate the same thing about the dummy variables, and we get this is insignificant and pretty bad estimate. Right? But we do it again, controlling for each student, it becomes quite significant. Okay. So usually when I look at these graphs, I don't interpret so much the coefficients on the individuals, because it's somewhat meaningless for us at least. But we focus a lot more on the treatment X. Okay. So here it's saying then that X does have quite a significant effect on the individual students. Okay, so that's great. Dummy variable approach is great, but it's a little bit cumbersome. So the fixed effect is essentially the same thing, but doing it automatically for you. So it creates a dummy variable for each group. Okay, so each time invariant predictors are then not reported for simplicity's sake. So if we run that, this is the code results on that. I'll skip over a little bit. It's pretty much the same thing, but it gives you it reports just the x and nothing else. Okay, so you can interpret the x, and if you look at the coefficient a couple slides ago, it's exactly the same. Okay, so essentially that's what the fixed effect does, is that just puts a dummy in for each student. Okay, so that only the time variant can be interpreted. Okay, okay. A little bit more complicated are random effect models. In practice, I actually rarely find these very useful, but I just want to kind of throw it out there. Random effect models is trying to capture, then explain the time invariance as well as the time variance. Right. So again, this is the thing like maybe try to explain is, does gender matter? Does height matter? It's hard to really tell because it doesn't change over time, right? But this, I just want to throw it out there. You can take a look. But there is a test, something called a Hausman test, that tells you whether the fixed effect or random effect models work better. Okay, and it basically says if the p-value, this is reported from R, if p-value is less than 0.05, then use fixed effects. In practice, I found about 99.9% of the time, fixed effects are always preferred. So, but just, you know, the other thing that I did, sometimes in my research, what we try to do is that we would report the main result as a fixed effect, and then we kind of say, okay, maybe there is something that's time invariance that we're interested in. We run the random effect models, and if the coefficients are stable, meaning the signs are the same and the significance remains the same, then we can interpret our time invariance. So it's all about, a lot of it's about stability of the statistics. Okay. Okay. So let's take a look at some examples of return on investment of user-generated content. Okay. So let's take an example. So I'll motivate some of these strategies using a lot of examples. Okay? A lot of it is based on retail because that's where it's been studied a lot. Education data hasn't been as readily available, but it is starting to. I'm hoping this workshop will kind of get more people excited about education data. Right? Okay. So let's say we want to interpret, do reviews cause people to buy products? Really positive reviews. Okay, that's a causal inference we're trying to make. The alternative explanation, possibly a reverse causal interpretation, is that users are happy with the product, and as a result, they write positive reviews. Okay, so you think about, you're going to Amazon, you try to buy something. Are you actually reading those reviews? The positive reviews are actually causing you to buy or not. Okay. But then there's a lot of unobservable data, such as like whether the firm did a lot of outside advertising, online or offline, to drive these sales. Okay. So we have, of course, there's also other things like product quality we can observe. Reviews may also not be true opinions of people. It may not review true quality, and there's actually quite a lot of selection bias. In my class, I always ask people how many people have reviewed a product online, and usually generally very few. Okay. Okay, and there's a lot of endogeneity. So that's a general context that we want to kind of motivate these identification strategies, something along these lines. Okay. So let's take a look at some common strategies. So one, of course, we could use fixed effects models, which we talked about. I'm going to talk about then next is difference in difference, regression discontinuity, natural experiments, and then propensity score matching, and instrumental variables. And so usually these, I would say, you can use them separately, or you can use some sort of hybrid mix of different methods and techniques. Okay. So we look at this UGC, user-generated content, with, let's say, sales and product reviews as an example. Okay. So in difference and difference, we try to construct two similar groups using our historical data. One, conceptually, we see this is the treatment group. This is our control group. Okay. And we can basically compare averages, compare average change over time of these two groups. Okay. And then it's nice because when we do that, we can control for a lot of time invariance of each. We need control for time invariance of the two groups, but also controls for time variance of the two groups. Okay. So if you have two groups that are kind of going simultaneously, right? One is that they somehow naturally got some sort of treatment. Then any weekly effects, seasonality effects, maybe it's like holidays, Christmas, Chinese New Year, sales may suddenly spike up. Okay, so when you do this difference in difference approach, you can control for all those observable and unobservable factors. So that only the treatment is left. Okay, so one of the best papers that's heavily cited is this Chevalier-Mason paper, looking at Amazon reviews versus Barnes & Noble's book reviews. Okay, and basically they said, okay, well the basic model is YIT is the number of sales of book I in period T. Okay, and then this is the general model is maybe there's some sort of treatment that happens in between the time period. So this is a binary 0, 1 after some T, whether that group was affected or not, 0, 1. And then we multiply the two together as saying this group was affected, and in that observation it was after the treatment. Okay, so that's a strategy that this Chevalier-Mason paper did. So here, do ratings cause sales of books on Amazon and on Barnes & Nobles? To scrape the data from the two sites, this is cross-sectional, unfortunately for them. But what's the challenge here is that really book quality is unknown. You don't know that Harry Potter book is really that great, right? If you look at sales, then that's a little bit tautological logic, right? You're saying sales represent it indicates the quality of the book, but then that predicts sales. That's very circular logic. Okay, so we cannot use that. But there's also other things like there's site differences. Maybe people who use Amazon are different than people who use Barnes & Nobles. Okay, and then maybe there's some sort of reverse causality. Again, if you like the book, you write positive reviews. It's not that causing some sales. Okay. But then the model they use then is something that looks like this. So they use the superscript A and B for Amazon versus Barnes & Nobles. They said, okay, there's some factors they take logs of this just because it's very skewed. But they look at the price of the book on Amazon, they look at the price of the competitor of Barnes & Nobles, and they look at some of the other factors in the reviews and the ratings of the books. Okay, but what's interesting, and then they did the same thing for Barnes & Nobles with the A's and B's swapped. But they're doing, what's interesting about this is that here they look at the same book across the two sites. So it's the same Harry Potter book on Amazon versus Barnes & Nobles. So they control it for book quality. Okay, and then secondly, then they also look at the site characteristics of the two sites. On average, Amazon reviewers they found were a little more positive than Barnes & Noble's reviewers. I think, if I remember correctly, it's been a few years. Amazon reviewers are like on average like 4, and Barnes & Noble's was like around a little bit less, like 3.5 or so. Okay, so that they're able to control for that with some of these variables as well, the site differences. Okay, and so what remains then is actually only any slight variation within that book for the different reviews. Right. So you know, for example, if you see, okay, on average, Amazon reviews are about 4 for all the books, and Barnes & Noble 3.5. For Harry Potter, there's the same book across both sides. Maybe on Amazon it received 4.1, but maybe on Barnes & Noble it received 3.4, so slightly below average. So you can then see the effects of the reviews on the sales. Does it actually impact the sales? Okay. So we have price vector review sites, and then shipping variables and other factors about the website itself, the e-commerce site. Okay. So the estimate basically is difference model. They're taking out the difference between how many quantities were sold on Amazon minus the number of quantities sold on Barnes & Nobles, and then they estimated this model, and they find that yes, there is a strong effect on reviews. Right. So they're also, by controlling for the book, they're also controlling for the reverse causality. That maybe it's a really good book, people come and review, give more positive reviews. Okay, so that's one very useful technique. Is a difference in difference type of approach. Okay. Next, we look at regression discontinuity. And here, again, we're trying to find this, this relationship between two variables, x and y, sorry, alpha and y. Okay. And so in another paper, they're taking advantage of rounding of stars. Right? So every, like I say, bookstore, you can rate like is a 4-star book, 5-star book, and so forth. But a lot of computer systems, they round it to like perhaps the nearest integer, or in this case, 0.5. So now it's like 3.5, 4, 4.5, 5. Okay. And so if ratings exposure, if being exposed to that rating affects demand, the number of cells, then rounding should cause some sort of discontinuous jump, right? So what that means is, if the book is say a 3.3, that's okay. The computer system will round it up to 3.5. So if people are reading the reviews, then this book that's actually only 3.3 in quality suddenly looks like 3.5. Then you should see a huge jump in sales because of this. Okay, that's exactly what they try to do. They try to say, okay, T is some sort of rating, and R is a binary variable, whether the stars rating that the buyer sees is rounded up or not. Okay, so the model is very simple. You just have, again, sales of IT, book I, in period T. And then this is the ratings, where it's like 3-star, 3.3-star, 3.6, and so forth, the actual rating. And then this is whether it was rounded up to, in this case, 0.5s or not. Okay. So this is still a working paper from Yelp. So this is what they see. Is that here's the sorry. Okay, this should be actually sales, and these are the ratings, right? And so if there was no effect, you would see a linear slope. It says, okay, a 3.3 book really has 3.3 equivalent of sales. Okay, but what you see instead are these jumps. So this is 2.5, 2.75, 3, 3.25. So here between 2.5 and 2.75, on the system it looks the same. It's rounded down to 2.5, right? And so the sales then it gets fitted to the step function. But then if your book is at 3.74 and then the next book is at 3.75, it gets rounded up. So then suddenly in the data they see a jump in sales at this level, and so forth. Right. So actually, what we've looked at some of the university data in US, we actually see this continuity in terms of honors degrees. So in Singapore, you have the old British system, like first-class honors for people who have GPAs of between 4.5 and 5. Second class upper class second upper is between 4 and 4.5, and then 3.5 to 4 and so forth. And we also have this salary surveys. We see that there are definitely these staircase jumps. If you're a student that's 4.9, your salary is not going to be that much different between a student with salary or a GPA of 4.5. Right? But there's a huge difference between 4.4 versus a 4.5 GPA when you graduate. Right? So this is telling us then that employers are definitely looking at GPA. Right? We can actually estimate the gap here and how much they care. Right? Okay. So the next thing is that conceptually sometimes I actually generally like this the most are natural experiments. And natural experiments is because it's something that kind of happened in the past, but you can use these blips in your data and your scenarios to better understand the units that you're trying to analyze. Okay. So here we said nature intervenes. It's exogenous. It wasn't some city planner that intervened. It was just unexpected. It wasn't correlated with your outcome. Okay. So it's great for when it's difficult to intervene. Events are unexpected or exogenous. Okay. So the assignment of treatment and control group should be somewhat random. And we'll talk about how we can handle non-random groups and whatnot a little bit. And then analysis becomes very simple. You just do a different diff, just like the Amazon and Barnes & Noble's example. Okay, but you conceptually we need to find these exogenous events, these natural experiments. Okay, so this is one of my papers. We look at do a lot of social network. So we look at how do people form friends, right? This has been always traditionally very difficult to draw causal analysis on, because you cannot do a lab experiment by forcing two people to be in the same room and say, now you have to be friends, and we track them over time and say, you have to go eat together and drink coffee, right? So there's very few cases where this is possible. But in this case, we say what are factors that cause friendship formation? Okay. Here we worked with Facebook data science team. We looked at 1.3 million college students in the U.S. And we look at 4 years, 133 universities, 4 years, user level aggregated number of post number of messages and number of friends in their networks. Right. So again, it's hard to test out. It's also specifically the mechanism. It's hard to tease out homophily, which are like people who have similar interests tend to group together. How do you sever this homophily? You're forcing people who are not similar to be friends, right? Okay, so we look at Hurricane Ike, second largest hurricane in the United States, and how it affected friendships over time, over several years, actually. So this is the rain path of Ike. It was hardest hit around Houston area. And then we looked at all the triangles, all the universities that we looked at. These are students who were enrolled in over 4 years' time at those universities. And the red ones were the ones which are most heavily hit. We added FEMA data, which is the Federal Emergency Management Agency, that gives out like zero interest loans for people to rebuild in disaster areas, right? So that confirms our red triangles. And then what we did is that we actually matched these universities to similar universities in the blue as our control group that were not affected by the hurricane. Okay? And so what we did then was that we look at network metrics. I won't get too much into detail about what these mean, but I just want to show you more about. So this is 4 years over time. The blue is the week of the hurricane, and then these are our metrics. So we look at degree, which is number of friends, right? That doesn't change too much. The blue is the control group. The red is the treatment group. Transitivity is another network metric, which is the number of triangular friendships that exist. This is one basically how strong is your community. The higher transitivity, the stronger close-knit the community, right? And we see that actually diverges quite a bit. So before the two groups are the same, and afterwards it diverged quite a bit. Right? So actually the hurricane caused different types of friendships to form as a result. Okay, and then we also do between us. But the point I'm trying to show you here more is that you can use these natural experiments to nicely control for these things where you cannot intervene. Okay. Okay. So as I mentioned here, one of the techniques we used was matching. We tried to form a control group. So we know the treatment, but how do we know that the control group is similar before the treatment occurred? So this is known as propensity score matching. It basically tries to find like a similar group of people using a scoring function. It's almost like a nearest neighbor. You're like a machine learning domain, right? So scores should include all the variables which can possibly affect the dependent variable, the outcome variable. Okay. And so here we identified 5 affected scores. We matched against 10 similar scores, and basically it's a logistic model that you predict the outcome. So here it's a logistic model where we put 0 and 1, whether they're in the treatment group or in the control group. And then we train it once, and then we predict it, pick the highest scores as the match sample, the match control sample. Okay. Okay. So this is just more showing you basically we try to do this. Red is our control group. Black is red is the treatment group. Black is the control group, and it should look balanced. So here this variable looks like it's on a straight line. So this is what we use for matching. These also are somewhat on a straight line. We use these for matching. There's many others in the paper where we look at it should be, if it's randomly distributed, like it's covered all over, then we don't need to use it for matching. Okay, that's one quick way of looking for what's called balance. Okay, and finally, we're doing pretty well on time. Okay, finally, another method that you can use for causal analysis is more instrumental variables. So one of the problems is that variables can be endogenous, which means that your x is a function of possibly other variables, as we showed with colliders and the networks of variables. Okay, And so technically, that means that the correlation of x to the error term is not 0. It's one way to really quickly identify heterogeneity. So then we can give you very biased results. Estimates are not correct. The betas are just completely wrong value. The p-values are not reliable. You just don't know what you're getting. Okay. So one approach then is try to identify another variable called z, such that z is not correlated to your error term, right? But it is correlated to your x. Okay. So if we do this, then we can say that. So now we deconstruct our original x in our original model as a function of some sort of new variable x hat and another error term b hat. But then our x hat then consists of another estimate of our z. Okay, so that's our z is to instrument. Okay, so basically this is kind of say that in endogeneity, this condition basically says that your x is still very untrustworthy. There's some variance in there you cannot explain, right? But it seems to be happening. So you try to find the z that can isolate all the variance of your treatment. Okay. And so, in reality, in practice, it's very difficult to find a good instrument, I would say, because it's not there. What would possibly even be a good instrument? Okay, but if you are able to find it, then what you can do is use a two-stage least square approach, or 3 stages, or you can do more complicated models. But the first step is then you try to predict x using your z. So here's your x prime. You predict it using your z and some other variables. Then you use that predicted x to fit into your original model. Okay? And then you can have a stronger causal inference on this. This is an instrumental variable approach. Okay, so there's a nice example of this in this paper on how Craigslist, which is like kind of like how would you say classified? Yeah, thank you. The classified ad site started like in '98 or something. They basically found that Craigslist causes STDs in cities in the United States. And if you use Craigslist, this is a precursor to many of the new sites. There's a lot of like dating ads on there, and a lot of like sketchy kind of prostitution and other things in there. And so they show that Craigslist causes HIV and STDs transmission. But the problem here is that it could be that X is correlated to Y. So here the treatment is kind of the introduction of Craigslist to a city. And the Y here is STDs, right? People believe maybe Craigslist chose cities that had higher STDs to enter in the first place, right? Or maybe ones that were like more liberal, more had a lot more drugs or whatever it is to choose those cities. Okay. So the causal inference it would be that it wasn't because of this, but it was just because of the introduction of Craigslist that caused increase in STDs. Okay. So what's the pseudo instrument on this? Oh, sorry. Sorry, I missed it. Right. Okay. So what they used was actually the cost of laying internet cables in the cities. Basically saying that that should be correlated to the trying to get this right here. So the cost of laying cables is the z, right? It should be correlated. Should not be. Try to get this right. Should not be correlated to STDs, right? But it should be correlated, highly correlated to adoption of Craigslist. Right, so the higher cost, less Craigslist. Okay, so they use that as an instrument, and they run this two-stage least square. They find that truly Craigslist does have an impact, most likely a causal impact on STDs. Right, so that's kind of a nice thing. Again, how would you run this in a lab? Can I just tell some city planners that we're going to test to see if Craigslist causes STDs? So can we please launch this application in your city? Right, that would never happen. IRB certainly would not approve of this. So that's all I have. I guess that's a little faster than I had planned, but that's fine. So hope you takeaways. Please don't be a deer lady. We like we like looking at data, but we need to really understand the full context to understand what's going on. Right. I'd be happy to take any questions, or we can start for lunch. Questions? Should be some of our PhD students should know this stuff already. Yes, they should be on the. We're updating the websites constantly. So sometimes the YouTube links are not working. Just refresh it, then you should get a new one. Okay. Yeah. So sorry, I forgot to introduce myself. So I'm Professor Tuan Phan, Department of Information Systems and Analytics. So that's in the School of Computing. We also sometimes IS is also sometimes in business school. So my training is more in marketing, but we are very strong on like identification issues. So I've been here for 6 years now, going on 7. So we're always looking at like new uses of really massive amounts of data sets, combining machine learning and identification. Right, so doing like image processing, doing a lot of voice, a lot of text, to add in as features of as an instrument or as other ways. So I think I look forward to start talking to Mihi Park here about some education applications, looking at some of the MOOCs data, and we'd love to see either through experimentation or through historical data on understanding some of the causal effects.
In time series data, don't you have to be careful to smooth out cycles?
Yeah, it's good. Yes, very good point. Yes. So 2 things. One is if you're using panel data, you have the control group and treatment group. So the time is already taken into consideration, because if the treatment, if both groups move at the same time, then that's a treatment, that's a seasonality thing. Right. But what we look at is really the difference between the control and the treatment group. So the time seasonality shouldn't matter. But if you only have one single metric, one group, there's no control group, then it's a problem. Yeah. But it didn't cover also. Sometimes we do quasi experiments. So quasi natural experiments are when you don't have a control group, but if you have substantial data before and after, then you can have some confidence that what you should see, marker here. Okay, maybe not. Is then if the treatment happens, then there should be just a break, just a step function goes up. Then you have confidence that that is something happening, right? So what you want to do is that then you want to fit 2 models, one model before the treatment and then one model after the treatment. But then that alpha, the difference between them, is the effect.
So would you use a dummy before and after to create that break? How would you fit the 2 models together?
Yeah, so you can do that. No, that's a good point. I actually have extra slides just to preempt that. Yes. Let's hit it in 1 minute here. Okay, so this is another study we looked at, was how people affect how Facebook privacy controls affects people's willingness to disclose data, right? And here, the same thing. They just released this control to everyone globally. So we didn't have a control group. Okay, so essentially, this is what we have. This is the red line is before, the blue line is the event, and then this blue line is after. So we have 3 different y variables here. And it's a little hard to see here, but there's actually a slight jump to fit the different linear models to this, right? To your point also is that there is some seasonality. So actually what we try to do is actually estimate this model. So we have after a dummy variable, that's t, that's after. And then we control some control variables, and then we have a monthly dummy to control for seasonality, right? And so anything that happens should be explained by this this variable, right? So this is a better shot of it. Is that then you see that there's quite a. So here actually I fit it to 2 separate models just to visualize it better.
Okay.
But even then, I think in most publications, even if you just show this graph, people would buy it.
Right.
As 2 separate visualizations instead of 1.
And how did you create that separate variable for the privacy?
Oh, so the event was the privacy event. So the context of this story was that the Facebook in 2009, Facebook launched the first major privacy changes. But they had you walk through this like dashboards. Say, do you understand this? This and this? Yes, yes, and yes. But the defaults before and after were the same, right? So objectively, they're the same. So the way it created this data was just observed a couple of. So here's the number of messages that people posted before and after. So I separated the data set just into 2 pieces, right? And then just fit one.
The same model.
That's right. That's right.
Separate data sets.
That's right.
One before.
That's right. So it was basically this model, but without this variable.
Right.
But I subset it into 2 different things and then visualized it. And then so here we also fit. So you can see the blue is the raw data. The gray then is just the polynomial fit of the raw data. The green is then we did the monthly dummies.
Right.
And you see actually the green dots. It's a little hard to see in the slide. Are the coefficients for that month. So you can see it kind of goes this way. And then the green is just the fitted for the seasonality.
So after the slope is more negative.
Right, correct. So then down here then is after it's been de-seasoned.
Right.
So we take the blue, we minus the green, and we get the red here.
Okay.
Right.
How do you do that? Pull out the seasonality.
Right. So right. Yes. So in R, then when you estimate this model, we get the betas. So the green dots here are the betas. So then we just predict it using this model. So we run a simple model without this, right? And then we get predicted values for the betas, and we subtract that from this y. So then what you have left is just this policy, right? So I guess I'll be happy to share the code and you can take a look at this. And then so if you look at this, it's actually roughly hovering around 0. Right. And then you can see that then the gap is a bit more apparent. It's smaller, certainly because of seasonality and all the stuff. So we do that so our main story is actually more on the number of posts. The gap is even bigger on this. Right. Yeah. And then here, it's even more interesting is that actually it changes the slope afterwards for this outcome variable. Right. So sometimes, I guess if you're a more strict economist, changing the slope is not a good thing.
Right.
Right. So yeah. So let's see. Yep. So yeah. So those are results. So this is our reported full model, full sample with the after policy effects. And then, so I'd say so usually you just plot it, people are happy with that. And then you run a simple model, and you show the p-value, and then you've sold them on it. Right. So, yeah. Okay. Thank you.